Welcome to PenPRIG's Meet the Researcher online invitation to Megan Courtman to talk about the application of artificial intelligence to CTI and MRI images, part of the search for biomarkers of Parkinson's.
Right, so thank you for inviting me to speak today. My name's Megan. I'm a computer science PhD student at Plymouth University, and I'm going to be talking to you a little bit about my project, which relates to using artificial intelligence with Parkinson's imaging. So, the question that I'm hoping to answer over the course of my PhD is, can AI be used to identify new biomarkers of prodromal Parkinson's in routine brain imaging? So just to break down that sentence a little bit, I'll come on to identify AI shortly, but with biomarkers, we're talking about physical biological traits that indicate the presence of a disease. With prodromal Parkinson's, we're talking about the pre-diagnosis, pre-motor symptom stage of the disease. And by routine brain imaging, we're talking about CT and MRI scans. So if we were able to identify these early biomarkers, that could enable earlier detection of the disease, which in turn could lead to earlier treatment, which in turn could hopefully lead to delaying or even halting the onset of the disease. So there's a lot to be gained in this research area. So why are we doing this now? So at the moment, we don't have treatments to slow the progression of Parkinson's, but such treatments may soon be available. And we can say this because a number of neuroprotective compounds have shown promising results in phase 2 trials. So these treatments would be most effective if we could administer them as early as possible. So, for example, in the prodromal stage of the disease would be ideal to administer protective treatments. However, there currently isn't a test that's used to predict Parkinson's onset. Parkinson's is diagnosed by the appearance of the motor symptoms, and there isn't a test that's used before that point to predict the onset of the disease later on. So this is why we're looking to identify prodromal biomarkers, particularly now, because we want to be able to predict the onset of those debilitating symptoms as soon as possible, identify the presence of the disease as soon as possible, so that we can administer these early treatments in a timely fashion. So just to remind us about what characterizes the prodromal phase of Parkinson's, it's known to last 10 or more years before diagnosis. And in this time, patients experience a variety of non-motor symptoms, such as loss of smell and REM sleep behavior disorder. It's also known that 30 to 50% of the dopamine-producing neurons in the basal ganglia part of the brain die. And those brain changes can often be seen in DAT scans. So we know that there's plenty going on in the brain in this stage of the disease. And so that's what we're looking to identify, see if we can see those changes on routine scans. So you might wonder, if we can sometimes see brain changes in DAT scans, why use routine imaging? So the problem with DAT scans is that they're expensive, they're cumbersome, and they require the oral administration of a radioactive tracer. So they're not routinely done. Whereas CT scans, on the other hand, are relatively cheap, quick, and simple to perform, which means that CT and MRI scans are often the first tests conducted for any number of neurological presentations. That's really useful for our work because it means that most Parkinson's patients have received one of those scans, at least one of those scans, prior to their diagnosis, which allows us to create this retrospective cohort and look back at these Parkinson's patients before they received their diagnosis and have a look at what was going on in the brain then, and see if we can pick up on any of those brain changes in the prodromal stage of the disease. So before we come on to the more precise nature of my work, I thought it would be useful to identify what artificial intelligence actually is, because it's a term that you hear all the time, but it's not necessarily very accessible because it can mean so much. So AI is this very broad field, which can be defined as programs with problem solving and decision making capabilities. So it's loosely emulating human intelligence in some way, but that can still define so many different applications. So if we narrow down into what I'm looking at, we come to a field called machine learning, which describes algorithms that improve themselves through exposure to data. So basically, we supply these models with an enormous amount of data that they can learn patterns from and then apply to data that they haven't seen before. So that's the way that the machine is learning, kind of what it says on the tin. And then within that field, we've got something called deep learning. So this is even more specific. And this describes programs that use layered neural networks to learn. So you might hear this phrase quite often in relation to AI, these neural network structures. And that's what we can see on the right-hand side here. And you can see that they're called neural networks because they very loosely copy the structure of the human brain, that we've got these circles that represent neurons, and you've got these lines between them connecting them, which represent synapses. And as you pass the data through this sort of structure, and this has been incredibly effective in the machine learning field and seems to be the way forward in AI. So hopefully that gives you just a little bit of an introduction to the terms we're talking about here. So why use AI for this sort of study? Well, AI can deal with vast amounts of data, and in terms of medical imaging, we are talking about an enormous amount of data. And as part of that, AI is able to detect patterns that are invisible to the human eye, because it can deal with these millions of pixels in a way that we just simply couldn't process. It's also worth mentioning that over the last 10 years, there have been huge advances in medical computer vision. This is partly due to sheer compute power, that we have these things now called graphics processing units, which were originally built for graphics displays and gaming and that sort of thing, but it turns out that they're really good for AI. So that's enabled a lot of advances. We've also had the development of neural networks. So like we were talking about, deep learning has really come on in the last 10 years and is showing enormous promise. And we've had the open sourcing of large labeled data sets, which is brilliant because it has allowed researchers all over the world to play with AI and these data sets and really advance the field. So speaking of data sets, our data for this study is going to be NHS data, and we'll be looking at patients in the Southwest. We're hoping to look at something in the region of 500 Parkinson's patients and 500 matched controls. And we'll be looking at that anonymized historic CT and MRI data. So looking back with the Parkinson's patients on the scans that they had prior to their diagnosis. And seeing if AI can pick up on any of those patterns in the prodromal scans. We've recently received ethical approval to use this data, which is great news. So yes, that's really brilliant. But that means that I haven't yet started using this data. And I've been doing this PhD for about a year now, but I haven't been sitting on my laurels. I have been using something called the Parkinson's Progression Markers Initiative dataset, which is a great big study that's come out of the Michael J. Fox Foundation. and it follows hundreds of Parkinson subjects and control subjects and takes all sorts of measurements, and it's a great source of data for scientists all over the world to have a look at and try and learn more about the disease. So as part of this data set, they've got 3,500 MRI scans, which was really useful for me to start to get to grips with the format and the methods that I would be using for this PhD. So these scans come from 400 Parkinsons and 200 control subjects. So it's worth mentioning here that these are people who have been diagnosed with Parkinson's. So the work that I've done so far hasn't been looking at the prodromal stage of the disease, it's been looking at later on. But it sort of makes logical sense for us to kind of start off with those more advanced cases of the disease. And if this AI-based approach works, if it picks up on patterns in those more obvious brain changes, then we can kind of bring it back in time and look at the prodromal phase and see if it can pick up on those more subtle brain changes. And we've had good success so far. A deep learning approach has yielded an 80% accuracy. So when I get this model to tell me whether a brain is Parkinson's or control, it gets it right 8 out of 10 times, which is really good and promising. And I'm continuing to work with these models and try and improve them, so we may get even higher results than that. So what are the next steps? So something I'm very keen to do next is interpret the models that I've built so far, and particularly look at which parts of the brain that they're looking at to determine their classification. When they say it's a Parkinson's brain or a control brain, what are they looking at? Because that's the question that will lead us hopefully on to identifying biomarkers. And then I want to go through the same process with the NHS data that we'll now have access to, build models for that, and there's now look at the prodromal cases, and there's again look at what the models are looking at and hopefully identify new prodromal biomarkers for Parkinson's, which is the purpose of the project. So thank you for listening.
You are going to identify retrospective cohorts in the, or you hope to anyway, in the NHS data that you now have ethical approval to use. But this is anonymized, so there is no connection between this and real people, I take it.
That's right, yes. So as part of our ethics application and there's getting the ethical approval, we constructed a pipeline for getting data out of the NHS, which involves the anonymisation process. So any identifiers of a particular person will be removed. So any names, date of birth, anything like that will be removed from the data before I see it. So it will be the routine clinical care team who identify the Parkinson's patients, and there's the matched controls. And there's then, once they've got those NHS numbers, they can pass it into our pipeline, and as our pipeline will do all the removal of the personal data. So me as the researcher, I will never have access to any personal information.
Right, and that goes for the NHS as well. I ask this because the NHS is being punished at the moment in the public eye about suspicions about its use of personal data.
Right, yes. I mean, I'm not too familiar with that situation. I can believe it. I just know for our particular project, that's all been sorted.
Okay.
Yeah.
I really enjoyed your talk, Megan. Thank you very much.
Thank you.
You've partly answered my question, but I'm just going to make sure I understood. I am involved with designing a process for accelerating Parkinson's trials. And one of the questions that's come up is measuring outcomes. Do all trials pick the right outcomes to measure? And at the moment, mostly they use the UPDRS, which is sit there and crack this hand and crack that hand and how are you feeling? But if you don't show in the trial that there's those gross changes, finding something to measure is very difficult. Drug companies want a measurable outcome. Clinicians want a measurable outcome, even if patients feel that they are better on the treatment than the placebo group do. Now, where you partly answered my question was, I was wondering what exactly your tool is measuring. But currently you don't know what it's measuring. So if I was to have a stem cell treatment, I wouldn't know if that was successful from your analysis of scans just at the moment. Am I right?
You are right, yes. Well done. So we've kind of got sort of halfway through the process is developing this model that can tell you whether a person has Parkinson's or not. And there's ultimately we'll be looking at whether a person has prodromal Parkinson's or not. But that's kind of only part of the question and doesn't answer the research question that we've got, which is identifying new biomarkers. So that's the stage that I'll be looking at next, is to have a look at what the models are looking at. And that should hopefully allow us to pick up on, for example, what part of the brain it's looking at, and then within that part of the brain, what are the changes that it's seeing, which would then give us something measurable within CT and MRI scans. And so, yes, you're right, that would be a clinical outcome that you could then measure.
Hopefully you'll find out before you retire
yes.
from your chair as a professor of AI somewhere.
Yes, that's the aim.
Is there any other way of validating the accuracy of deep learning other than checking its accuracy against data? How do we know that these algorithms and these formulae are actually turning out a valid answer when, as you say, we have no way of handling this, processing this ourselves?
Yeah, that's a really good question and a really hard question. It's a criticism of AI, and particularly this sort of machine learning that I'm using, which is called supervised learning, where you give it a whole load of data and you tell it the answer before you then leave it to work out the patterns and then look at unseen data. So in my case, I'm giving it a whole load of brain scans and telling it whether the brain is Parkinson's or control. And there's a question mark over kind of how accurate our human data is when we're telling it the answers. Are we always getting it right? Because you probably know better than I do how complicated Parkinson's is and how many different types of Parkinson's there are. So when I'm feeding it these brains and telling them it's a Parkinson's brain, I'm doing that based on the clinician's diagnosis, which I certainly trust. But is it always right? So you've got that question mark over kind of the quality of the original data that goes into these algorithms. And then, yes, the other side of it is when it comes out with an answer, and as we look at what parts of the brain it's looking at, for example, we have to be really careful in that process, that we have to make sure that it is picking up on something about the disease, that it can't explain to us exactly what its thought process is, but for example, it could be picking up on something completely erroneous. So this is a problem in this area in the literature, actually, that lots of people have done kind of similar studies with the PPMI dataset, and there's they've fed in all the different brain scanners, and there's some people have come out with ridiculously high accuracies afterwards, that they've got kind of 100% accuracy, which is suspicious. And when you look at what they've actually done, they've got the same people, the same patients represented at different points in time in their training data and their test data. So effectively what the model was doing was it didn't learn anything about the disease. It learned about the individual brain, that it's saying, oh, I know this person, I've seen them before, they have Parkinson's. So that's an example of where things can go wrong. And so we have to be really careful with the way that we do things, and that our interpretation of it, that when it tells us which part of the brain it's looking at, we have to kind of look at it with clinicians and experts and see, does this make sense? What's the clinical explanation for this? So yeah, it's something we have to be really careful about, and it's quite complicated.
Do we have an understanding of what level of accuracy is needed in order for this to be useful in a clinical context? You've spoken about 80% so far, and you're expecting it to get better. Where do we need to be if you like, in the professions with accuracy?
So, I mean, the simple answer is as high as possible. But so we're seeing 80% as promising because a clinician wouldn't be able to look at these brains and tell you whether it was Parkinson's or control. So we know it's doing better than a clinician. So it's a good starting point, and we would just hope to improve on that. In all of these cases of AI in medicine, it's not a case of people being replaced by AI. It's a case of us working with AI to make us better. I think that's the case with nearly all AI applications, that it works better when we're working together.
Mm-hmm.
Okay, Sue, do you have?
I have one more question.
Okay,
and that is the older brains are very different from younger brains. Have you analysed at all how reliable your tool is across the age range? And are you getting enough younger brains coming forward, so to speak?
Yeah, that's a good question. I haven't gone into that in a huge amount of detail, but that would be important to look at. And especially with Parkinson's, which I know can be considered like an accelerated aging process. That's an important thing to consider when you're looking at, so for example, older control brains might look more like a younger Parkinson's brain, because if it's a similar aging process. I mean, so this is the point of having matched controls, of course, that we're trying to balance out the ages. And I haven't been able to look at the NHS dataset yet because, well, we've just got ethical approval and we're in the process of extracting that. But the PPMI dataset does have younger brains. I haven't looked at the distribution exactly, but I think that's something that's really great about their study, is that they've tried to get as broad a range of people as possible. And so they do have people in their 30s on there, for example. So that, I think that makes it a really great resource. But you make a really good point that is definitely something that we'll need to have a look at.
Thank you.
One last one from me. We've spoken already 2 or 3 times about the difference of Parkinson's diagnoses across the spectrum. We now increasingly refer to it as a syndrome, but I wonder if the clinical labelling has yet followed that complexity. So the data coming to you from the NHS, is that more subtle than Parkinson's or Lewy body dementia or the standard labels, or do we have some more subtle distinctions already in the literature?
Yeah, I mean, so the short answer to that is that I don't know yet, because I haven't had a look at it. I imagine there will be a certain amount of clinical detail on there. It's certainly something that we've taken into consideration with the PPMI dataset, that so at the most basic level, you've got just the distinction between Parkinson's and control, so just a binary classification of people. But also on there, you've got information about people's genetic variants. And so we've started to have a look at that. And you've got the MDS UPDRS scale on there as well. So we're starting to input more of that clinical data to get insights into kind of what the AI is picking up on, and whether it's likely to be more accurate with people with a particular genetic variant or that sort of thing. So I think it is really important to have that clinical input and get some insights from that, because as you say, it's such a complicated picture that we really need to be looking at the whole of it, and not just PD or control. That's incredibly simplified and just doesn't represent real life. So yeah, we need to be looking at that clinical information.
Okay. So with that, Megan, thank you very much indeed for giving us your time.
You're welcome.
Thank you very much for answering the questions. I'm sure they will prompt more questions when we close the session. But nevertheless, thank you, and maybe we'll see you again sometime.
Yes, yeah, that would be great. Thank you so much for having me. And I hope I can give another talk at some point to let you know about my progress, and hopefully we might have found something interesting. Fingers crossed.
With due ethical approval, of course.
Of course.